Let's consider how to analyze the data from the ADHD treatment case study. These data consist of the scores of 24 children with ADHD on a delay of gratification task. Each child was tested under 4 dosage levels. In this section, we will be concerned only with testing the difference between the mean and the placebo condition and the mean and the highest dosage condition. This difference between means should not be tested the same way you would test the difference between 2 independent groups. Since the scores in the placebo condition are from the same subjects as the scores in the highest dosage condition, the assumption that the scores are independent is violated. This figure is a scatter plot showing the scores in the highest dosage condition, D60, on the y-axis, and the scores in the placebo condition, D0, on the x-axis. It is clear that children who got more correct in the D0 condition tended to get more correct in the D60 condition. The correlation between the two conditions is high, R equals 0.80. Clearly, these two variables are not independent. To conduct the significance test, compute the difference between the D60 and the D0 conditions for each child and test whether the mean of these different scores is significantly different from 0. The different scores are displayed in this table in the column D60 minus D0. The mean of the different scores is 4.96, the standard deviation of the different scores is 7.54, and the standard error of the mean of the different scores is 1.54. The t-value is 3.22, and p is equal to 0.0038, so the mean difference score is significantly greater than 0. Therefore, the difference between the D60 and D0 conditions is significant. This t-test has various names, including correlated t-test, related pairs t-test, and t-test of difference between dependent means. If you had mistakenly used the method for an independent group's t-test with these data, meaning that you forgot that the subjects contributed scores in both the D0 and D60 conditions, you would have found that t equals 1.45, degrees of freedom equals 46, and p equals 0.15. That is, the difference between means would not have been found to be statistically significant, even though the difference was significant when the appropriate test, the correlated t-test, was used. We just showed how the correlated t-test returned a larger t-value than the independent group's t-test did. This is a typical result. Correlated t-tests almost always have greater power than independent groups' t-tests. This is because in correlated t-tests, each different score is a comparison of performance in one condition with the performance of that same subject in another condition. This makes each subject their own control and keeps differences between subjects from entering into the analysis. The result is that the standard error of the difference between means is smaller in the correlated t-test, and since this term is in the denominator of the formula for t, this results in a larger t. To see why the standard error of the difference between means is smaller in a correlated t-test, consider the variance of different scores. The formula for the variance of different scores is shown here. The variance of the difference between the scores in two conditions, x and y, is the variance in the first condition, x, plus the variance in the second condition, y, minus twice the product of the correlation, the standard deviation of x, and the standard deviation of y. Therefore, the higher the correlation, the lower the variance of the different scores. For the current example, r equals 0.80, and the variance of the differences is much smaller than the variance of D0 or D60. The smaller variance of the difference scores leads to a smaller standard error of the mean, which leads to a larger t.